Hello friends, welcome to GSR ChemTube channel. In this video, we are going to discuss about atomic structure chapter from this Planck's quantum theory. Before learning about Planck's quantum theory, let us know few things here. As progress in science field was happening, Maxwell's suggestion about the wave nature of electromagnetic radiation was helpful in explaining the phenomena such as interference, diffraction, etc. However, he failed to explain various other observations such as the nature of emission of radiation from the hot bodies, photoelectric effect, that is, ejection of electrons from a metal compound when electromagnetic radiation strikes it, and the dependence of heat capacity of solids upon temperature, and line spectra of atoms, especially for hydrogen. So these all phenomena were not explained by Maxwell's suggestions. Let us see what is blackbody radiation. When certain energy falls on the surface of a body, a part of energy is absorbed, a part of it is reflected, and the remaining is transmitted. All the incident radiant energy is not absorbed completely by the body because ordinary bodies are not perfect absorbers of radiant energy. However, an ideal body is expected to absorb completely the radiant energy falling on it. Such a body is said to be a black body. This phenomenon couldn't be explained with the help of Maxwell's suggestions. Hence, Planck proposed Planck's quantum theory to explain this phenomenon. In order to explain blackbody radiation and photoelectric effect, Max Planck in 1901 presented a new theory which is known as Planck's quantum theory of radiation. According to this theory, the smallest packet of energy is called photon or quantum. Substances absorb or emit light discontinuously in the form of these small packets or bundles. The radiation is propagated in the form of waves. The energy of quantum is directly proportional to the frequency of radiation. That is mathematically represented as E is directly proportional to nu. Thus, the energy of a quantum is given by the formula E is equal to h nu, where we know nu is c by lambda. This can be written also as hc by lambda, or 1 by lambda we know as nu bar. It can be taken as even hc nu bar also. So these are the formulae to calculate energy of quantum, where h is called constant known as Planck's constant. Its numerical value is taken as 6.625 into 10 to the power of minus 27 erg second, or 6.625 10 to the power of minus 34 joule second. And E is energy of the radiation in terms of X or joules. C is velocity of light. Its value is 3 into 10 to the power of 10 centimeters per second, or 3 into 10 to the power of 8 meters per second. Nu is frequency of radiation, lambda is wavelength, and nu bar is a wave number. A body can absorb or emit energy in whole numbers of quantum. As we know, quantum energy is h nu, so the number of quantum's energy is taken as E is equal to nh nu, where n is the number of quantum and h nu is the energy of each quantum. Let us see a solid example on this photoelectric effect. Here is a question given like this. A green light has a wavelength of 525 nanometers. Determine the energy for the green light in joules. So the wavelength of a green light is given as 525 nanometers and asking to calculate the energy of that light in joules. Let us see the solution for it. To find the energy, as we know that E is equal to h nu, or E is equal to hc by lambda, or E is equal to hc nu bar. But here they ask you to calculate energy by giving wavelength. So we can use the formula E is equal to hc by lambda, where h and c are constants. Lambda is the wavelength whose value is already given here. So let us substitute these all values in the formula. H value, that is Planck's constant value, is 6.625 into 10 to the power of minus 34 joule second, and the value of C, which is velocity of light, that is 3 into 10 to the power of 8 meters per second, and wavelength 525 nanometers. Here we have converted this nanometers into meters by multiplying 10 to the power minus 9 meters. By this calculation, we get the value of energy as 0.0378 10 to the power minus 17 joules, or 3.78 into 10 to the power minus 90 joules. And thus, a green light has a wavelength of 525 nanometers, has an energy 3.78 into 10 to the power minus 19 joules. In this way, we can calculate the wavelength or frequency or energy or wave number by using these relations. If one quantity is given, we can calculate the other. Thank you for watching our video. Please subscribe our channel and press the bell icon for receiving latest updates.